Hello, my name is William Alexander. I will be presenting our video lab today as a representative of my lab group consisting of myself, Edmund Ho, Crescentia Sugiyama, and Diana Lau. Our lab today is Lab 2, Voltage and Electric Field in a Coaxial Cable. Our hypothesis for this lab is that we can determine the linear charge density in a wire through two different methods, and from those two different methods we should get the same or similar result. Our methods that we are testing are derived, the first one is derived from the Gauss law, where the electric field in a coaxial cable is predicted to have the form ER equals lambda over 2 pi epsilon naught R times R hat. And lambda is the linear charge density on the central wire, and E naught equals 8.8542 times 10 to the negative 12th power C squared over NM squared, which is a physical constant called the permittivity of free space. And our second method is from the definition of the electrostatic potential, where the voltage is predicted to have the form of VR equals lambda over 2 pi epsilon naught times log R naught over R, where R naught is the distance from the central wire to the inner surface of the shield, and log is the natural logarithm function. So, our lab equipment consists of this virtual lab simulation, wherein we have a central wire and a shield, and our electric field will emanate from the central wire out and will terminate at the shield. So, for our experiment, we set our power supply to 15 volts. So we get to 15 volts by turning first the big knob, and then the fine-tuning knob will get us right to 15. So this virtual lab works by you set your voltage, then you can take a voltmeter here representative and see outside of the shield we have 0 volts registered. When we come in, closer we are to the central wire, the stronger our readings are, and the farther out we go, the weaker they get until they terminate at the shield. So here is our ruler, and we'll take a measurement here from the inner surface of the shield to the central wire. That is 5, 6, 7, 8 centimeters about. So we will take our measurements in those 8 centimeters. We will go half a centimeter per measurement, which you can very easily do by holding down the shift key and using the arrow keys to move. You see, we move half a centimeter whilst doing this. So you can set down points for your measurements by pressing the M key. So we just go along setting down our points for our data. And if we mouse over these points with the voltmeter, we have our voltage. So as we can see here, at half a centimeter away from the central cable, we have 12.43 volts registering. At 1 centimeter, we have 2.41 volts. A centimeter and a half, 8.86 volts, and it decreases as we go further along. So now we begin entering our data on our data table, which I've set up here. We have places for radial distance and voltage. Well, for radial distance, we start at 0.5 centimeters. We continued in half centimeter integrals, and we can just get Excel to copy that all the way down. And so for our voltage here, we will need to get that off of here, but in the interest of saving everybody time, I'm just going to copy it off of our already existent data from the completed lab. And our uncertainty for the data here for the radial distance is 0.25, and for our voltage it is 0.01. And that is true of all points. Now that we have our data, we will analyze it to come to our conclusions. So first, we will derive R naught from the equation R naught plus 1. No, R naught equals R naught plus 1 plus R naught over 2. We'll realize that through equals B5, which is 0.2. Well, no, R 0.2 plus B4, which is R 0.1, divided by 2. And we shall try to carry that through all of them, and there we go. We have R naught for each point. Although, as you can see here, we're getting a funny reading because there is not a B20, which is my bad. So fix that by just having this point here. We won't use it for data, but just for our R naught here. And now we will need to find our electric field, which is volts over centimeters. We would do so with the formula negative Vn plus 1 minus Vn over Rn plus 1 minus Rn. So, equals negative D5 minus D4 over, that is B5 minus B4. I think that's a mistake in parentheses. There we go. And we copy that down, and we have our electric field. And finally, we do not exactly need Rn, we need 1 over R naught. And the formula for this is quite simple. We simply divide 1 by our R naught equals 1 divided by F4. We carry that down, expand this a little. I'm not sure if I like all those decimals after it. So let's set our decimal places to 3. And that is much neater. And now we need to take the natural log of R naught over R, which in Excel will be equals Ln 8.5 is our R naught. That's the distance from the central wire to the outer edge of the ring divided by our distance, which is B4. We carry that down, and there we go. And now for our VR in volts, that is quite simply our data right over here. We just need to copy paste that over. Alright, now we're ready to graph our results. So I'll go to Insert Chart, XY Scatter Plot. Our data range, first we're going to use Calculation Table 1, which will use E in R, our electric field, against our 1 over Rn. But that is not quite right. We want to switch our X and Y values. Our X value, well, let's start with the Y. Our Y value shall be our electric field. Our X value shall be our 1 over Rn for E in R versus 1 over Rn. And here's our chart. Let's resize it a little smaller. Oh, and let's label our axes. Here we go. And the value of our x-axis is 1 over Rn. Value of our right axis is E and R. And there we go. We have ER plotted against R 1 over Rn. But we want a trend line. We want to see what the slope of our trend line is. So here we go. We simply add trend line, add linear trend line. There we go. We got a trend line going through all points. And we display our equation on the chart. And I had forgotten to set our y-intercept to 0. I've now fixed that, so there we go. There is our slope. And now it is time for our second graph. So we will insert chart, another XY scatter plot. We'll use and let's see, we want volts versus log. So I believe this time it's the right way around. 141 to 141, yes it is. So we have V versus log R naught over R. RY is volts. And our X is log R over RO. No. R, not over R. And here we go. I'll resize it a little bit. And same as before, we'll add a trend line. We will display our slope. And this time make sure the intercept is set to 0. And there we go. And I'm going to spare typing in those complicated equations and just go to our already completed data set, which incidentally is a little prettier. Our linear charge density from V versus log ROR. 2 times pi over epsilon naught times our slope. And similar for our electric field linear charge density. So as you can see, our numbers are fairly close, but not quite there with our uncertainties. I would say that we reached at least weak agreement with our hypothesis. There is, some room for leeway here. One of our equations can only be approximated, given that we're trying to compare vectors to static numbers. So I would say we're at least with weak agreement. We come pretty close with our two methods. So that was our experiment. So thanks for watching.